alaikum. I am MD Nuhi. Today, I am going to present our research work on the following topic titled as Continuous Wavelet Transform Spectral Image-Based Epileptic Episode Classification. These are the outlines of my research. Introduction. What is epileptic seizure? Improper and surplus discharge of electrical signal in the brain leads to epileptic seizure. Approximately 1% of the world's population is affected by epileptic seizure. It has 3 to 6 times greater risk of premature death. What is EEG signal? The electroencephalogram signal records the electrical activity of brain. The signal intensity is measured in time in terms of microvolts. These are the literature review we used for our research. Fatma et al. Proposed a seizure classification method using Lyapunov exponent and Ullmann arrays. The authors obtained a 96.79% accuracy in their classification. Their research lacks no signal pre-processing stage and lower accuracy. Tijan et al. Proposed a time frequency domain analysis with artificial neural network to detect and classify epileptic seizures with 99.28% accuracy. Their research lacks they only done binary classification here and no signal pre-processing stage was used. Umut et al. Presents a DWT decompose technique to decompose the EEG signal and KNN was used for clustering the wavelet. Their design model obtained 96.67% accuracy. Rashik et al. Proposed a complete ensemble empirical mode decomposition with adaptive noise-based EEG classification technique. Their design model obtained 99% accuracy, 99% sensitivity, and 99.5% specificity. They used complex classification procedure. Inisi et al. Proposed a genetic algorithm-based feature extraction technique. They obtained accuracy of 97.3% for KNN classifier and 89.7% for decision tree. They also have lower accuracy and used complex classification procedure. Mamun et al. Proposed statistical feature-based seizure classification along with ANNs. They obtained 80% accuracy for seizure classification. Wang et al. Developed a weighted Blake artist-based KNN to diagnose epilepsy and achieved an accuracy of 99% for three-class classification. They only used frequency domain analysis here and used complex classification procedure. Motivation. As epilepsy is a severe neurological disease, detection and classification of this disorder is necessary. Complexity for detecting epileptic seizure from previous research. Lower accuracy rate of several researchers. Curiosity for electrical activity of brain. Objectives. To analyze the raw EEG data in time frequency domain using continuous Wavelet transform to create an image dataset from spectral analysis of EEG signal in time frequency domain using CWT to extract deep features from the signal using the proposed deep ensemble epileptic seizure classifier to measure the performance evaluation metrics, that is precision, recall, F1 score, and accuracy of the design classifier. Finally, classifying multi-class epileptic seizure. Materials and methodology. Acquisition of EEG data. The EEG data is collected from publicly available dataset from the University of Bonn. It consists of 5 sets of data indicated as Z, O, N, F, and S. 100 single channel data segment. Each regulating time is 23.67 and sampling rate of 173.61 Hz. The overall description of the data is shown in this slide. Contribution of this research. The major contribution of this research is to create an image dataset from raw EEG signal using CWT spectral analysis. Another contribution of this paper is to modify 3p10 CN architecture. 3 extra layers are added at the bottom of this network. Finally, these modified models are ensembled to improve the classification accuracy of the epileptic seizure. Summary of the process model. Figure 3 shows the overview proposed seizure classification model. At first, the raw EEG data is analyzed using time frequency analysis, that is continuous Wavelet transform, to create the image. Then these images are used as a input at the classifier that we designed as deep ensemble epileptic seizure classifier. Then we measure the performance metrics of this classifier. EEG signal to RGB image creation. As the dataset contains 5 data packs, so total 500 individual data segments. Each data segment comprises 4097 data samples for 23 seconds. This proposed method segments these 4097 data samples into 16 chunks. Each chunk contains 256 data sample for 1.475 second. Total 8000 data chunks. In this research, only ZNS segments are used, so total 4800 RGB images are used. Figure 4 shows the overall proposed method for EEG to RGB image creation. CWT used for image creation. Table 2 shows the overall image created for different class using continuous Wavelet transform. Augmentation of image data. The data are augmented to create artificially generated new data point from the existing data to reduce overfitting. Table 3 shows the parameters used to augment the data. As we use transfer learning, we use three pre-trained model, that is DenseNet 169, DenseNet 201, and Inception V3, and we modified these three model for our classification problem. The total parameters and tenure parameters of the pre-trained CNN are shown in table 4. As ensemble models is used here, we used weighted ensemble. Algorithm 1 descriptively shows the weighted ensemble process of the base models. Proposed framework after image creation. The dataset was split into testing, validation, and training set accordingly as 10% for testing, 10% for validation, and 80% for training. Three already pre-trained models, including DataSet 169, DataSet 201, and Inception V3 were used as the base model. And we added three extra layers at the end of this model, that is global average pooling layer, a dropout layer, 30% dropout, and a dense layer. The model was trained across 50 epochs. Base size was 16, seed was 46, and learning rate was 0.001. Figure 5 shows the framework for Caesar classification after the creation of image. Performance parameter evaluation. It includes accuracy, precision, recall, F1 score. Result and discussion. Figure 6 shows the validation and training accuracy of modified DataSet 169, modified DataSet 201, and modified Inception V3. It is clearly shown from the accuracy curve that the validation accuracy is much higher than the training accuracy. It shows that our model is not overfitted. The enriched data in this work was fitted to the three base models to transfer learning. It is seen that accuracy increases with increment of the epoch. Figure 7 shows the validation and training loss of modified DataSet 169, modified DataSet 201, modified Inception V3. Figure 8 shows the confusion matrix for deep ensemble epileptic seizure classifier. The confusion matrix probably shows the misclassification properly. The proposed deep ensemble model provides the best classification result. The weight in this case was taken here, shown properly. Table 6 and Table 5 shows the performance evaluation of DenseNet 169 and DenseNet 201 for each class, that is precision, recall, and F1 score for each of the classes. Table 7 and 8 shows also the performance evaluation of Inception V3 and proposed deep ensemble epileptic seizure classification model. Table 9 shows the overall performance evaluation, that is weighted average. It is seen that the proposed deep ensemble epileptic classifier provides a very good result here. Comparison of accuracy with some recent work. All the authors use the same data set, and it is seen that our proposed model achieved 100% accuracy for classifying epileptic seizure. Conclusion. Identifying and categorizing epilepsy is essential since it is a neurological condition that makes human being disabled. This article improves the classification of epileptic episode. The image-based procedure was used to classify seizures to improve their accuracy significantly. CW-based spectral image provides significant information about the seizure. Finally, the proposed epileptic seizure classification method provides best result as it is weighted ensemble model. Using this model, we can achieve 100% accuracy, precision, recall, and F1 score. In the future, the model might also be used to diagnose conditions like Alzheimer disease, sleep apnea, etc. These are the reference we used for our presentation. Thank you.